Bismillahirrahmanirrahim. I am Dr. Muhammad Ajmal, and this is my second lecture on colloids. This topic is from the course of Advanced Physical Chemistry with course code CHEM 3117. The key concepts of this lecture are color of soles, then optical properties of soles, kinetic properties of soles, and electrical properties of soles. First of all, let's recall some basic terms which I have discussed in the last lecture. The true solution, suspension, and colloid. It was discussed in the last lecture that these three systems are actually two component systems. It means each of these three, whether it's true solution or it's suspension or it's colloid, it's a two component system where one component is the disperse phase and the other component was named as dispersion medium. And these three different systems can be differentiated from each other depending upon the size of disperse phase. As in case of true solutions, the particles of the disperse phase, diameter of the particles of disperse phase was in the range of 1 angstrom to 10 angstrom, while the systems or the two component systems having the diameters of the particles of the disperse phase in the range of 10 angstrom to 2000 angstrom were named as colloidal solutions or colloids, and the systems where the particle size of the disperse phase was greater than 2000 angstrom was named as suspension. So it means our major focus was on colloid. So colloid is a two component system where one of these component is named as disperse phase and the other component is named as dispersion medium. I have also discussed the types of colloids in the last lecture. Let's also go through these types and then we will move forward. These are the types of colloids based on nature of dispersed phase and dispersion medium. Colloidal system, as already discussed, is made of a dispersed phase and the dispersion medium. Because either the disperse phase or the dispersion medium can be a gas, liquid or solid, therefore there are 8 different types of colloidal systems. The ninth one, which is a colloidal dispersion of one gas in another gas, is not possible since the two gases would give a homogeneous mixture, and a system which is a homogeneous system that cannot be named as a colloid. So this table is representing different types of the colloids based upon the nature of the disperse phase and dispersion medium. We have 8 different types of the colloids. The first one is foam. This is produced when dispersion medium is liquid and dispersed phase is a gas. The second one is solid foam, and this is produced when a gas is dispersed in solid. The next one is aerosol. This is formed when the dispersion medium is a gas and dispersed phase is a liquid. The next one is emulsion, which is formed when dispersion medium is a liquid while the dispersed phase is also a liquid. We have to study some detail about the emulsion as well. The next type is solid emulsion. These are the dispersed phase with liquid and dispersion medium of solid. These solid emulsions are also named as gel. The next type is smoke. This is produced when dispersion medium is gas and dispersed phase is solid. And the next one is sol. Soul is a colloidal system in which dispersed phase consists of solid and dispersion medium is a liquid material. The eighth one is solid soul. Here a solid is dispersed in a solid. It means both the dispersed phase and the dispersion medium are solid materials. The most commonly used colloids are those where a solid is dispersed in a liquid. It means the dispersion medium is a liquid while the dispersed phase is a solid. And this system is also quite similar to the true solutions. However, to distinguish the true solution from the colloidal solution are mostly named as soul. And this soul further can be classified into different classes depending upon the nature of the dispersion medium. For example, a soul or a colloidal system in which water is used as a dispersion medium, that is named as hydrosol or aquasol. Similarly, if the dispersion medium is any alcohol, then the sol or colloidal system is named as alkosol, and if the dispersion medium is benzene, then the sol is named as benzosol. And now the properties of these sols. The first one is color. It's the characteristic of the sols that the sols have different colors. The first point is the sols have some specific color, and the second is a same sol may have different color when particle size of the dispersion of the dispersed phase is different. It is discussed in this table. Starting from the color of a hydrophobic sol depends on the wavelength of the light scattered by the dispersion particles. It means this is also a characteristic of the sol that when light falls on the sol particles, then it is scattered. This scattering is responsible for the color of that sol, and the color is further originated from the wavelength of light which is scattered from the soul particles. So the wavelength of the scattered light again depends on the size and nature of the particles. It means if the particles have different sizes, then they will exhibit scattering of different of radiations of different wavelengths. And similarly, if the two materials have same particle size but they have different nature, for example, one colloidal system is of silver and the other colloidal system is of gold. Both of the silver or gold particles have the same diameters, but this time due to difference in their nature, the color of the soul will also be different. So for example, in case of silver sols, variation in color as a function of diameter of silver particles is given in the following table. This type of color changes produced by varying the size of the particles have also been observed in many other cases. For example, in case of gold, in case of palladium, in case of platinum particles, and in many other systems as well. And this table shows that when silver particles have diameter around 6 cross 10 raised to power minus 5 millimeter, then the sol appears as orange yellow. And when the particle size is increased from 6 to 9 cross 10 raised to power minus 5 millimeters, then the color of the sol changes to orange red. And when the particle size is further increased to 13 cross 10 raised to power minus 5 millimeter, then the color of the sol becomes purple. And if the particle size is increased to 15 cross 10 raised to power minus 5 millimeter, then color of the same sol will be violet. It means a same material may have different colors when it is in the form of soles and have different uh, size of the particles. And now the optical properties of soles. The first optical property of the sole is Tyndall effect. The soles exhibit Tyndall effect. Actually, when a strong beam of light is passed through a sole and viewed at right angles, the path of light shows up as a hazy beam or a cone. This is due to the fact that sole particles absorb light energy and then emit it in all directions in space. This scattering of light, as it is called, illuminates the path of the beam in colloidal dispersion. This phenomena of scattering of light by the sole particles is called Tyndall effect, while the illuminated beam or cone formed by the scattering of light by the sole particles is often referred as a Tyndall beam or Tyndall cone. This is also shown in this figure where light is being illuminated. The colloidal particles or the sole particles may be at the bottom, and from this bottom the light is being scattered, and the scattered light as extends into the atmosphere, then it forms a cone like structure as shown in this figure. The scattering of light is also been demonstrated in this figure where one beaker contains a true solution while the second one contains the sole. In case of true solution, there is no light scattering, so there is no Tyndall effect, while in case of sole, the sole particles scattering the light. Actually, these particles first absorb the incident light and then they emit light in all directions as it has been demonstrated in this figure. When this light is uh, emitted from the collider from the sole particles in all directions, then it's known as the collective phenomena of absorbing light and then emitting it in different directions is known as Tyndall effect. The hazy illumination of the light beam from the film projector in a smoke-filled theater, or the light beams from the headlights of a car on a dusty road are familiar examples of Tyndall effect. If the sole particles are large enough, the sole may even appear turbid in ordinary light as a result of Tyndall effect. The true solutions do not show Tyndall effect as it was discussed in the previous slide. Since ions are solute, let's see why these true solutions do not show the Tyndall effect, or what's the reason that true solutions do not show the Tyndall effect. The reason is, in case of true solutions, the ions or solute molecules are too small to scatter the light. The beam of light passing through a true solution is not visible when viewed from any side at right angle. Thus, Tyndall effect can also be used to distinguish a colloidal solution from a true solution. The second optical property of the soles is ultra microscope shows the presence of individual particles. Sole particles cannot be seen with a microscope. The Tyndall phenomena was used to set up an apparatus named as ultra microscope. An intense beam is focused on a sole contained in a glass vessel as shown in this diagram. The focus of light is then observed with a microscope at right angles to the beam. This has also been demonstrated in this figure. This upper direction where the microscope is written and a symbol of eye is also drawn above this beaker. So individual soul particles appear as bright specks of light against a dark background. That dark background is actually the dispersion medium. This is what we observe in an optical or in an ultra microscope. When we look into the ultra microscope, then if the system contains colloidal particles or Sol particles, then bright specks are appeared. It means bright colored particles, they may be in spherical shape or in any type of particulate shape, they may appear in uh, the eye of the microscope. So it may be noted that under the ultra microscope, the actual particles are not visible. पार्टिकल्स को हम यहाँ पर नहीं देख सकते, लेकिन हर एक पार्टिकल क्योंकि लाइट इमिट करता है, तो हम जस्ट ये देख सकते हैं कि लाइट का एक ग्लो डिफरेंट जगह पे जो है वो लाइट ग्लो हो रही है. तो लाइट की जो ग्लोइंग है, दैट एक्चुअली means that particles are present over there. So it's a larger halos of scattered light around the particles that are visible. मीन एक पार्टिकल के अराउंड एक स्पेसिफिक डिस्टेंस तक उसकी जो लाइट है वो इल्यूमिनेट करती है. तो इस वजह से हमें जो अल्ट्रा माइक्रोस्कोप में जो ब्राइट स्पेक्स नज़र आते हैं, वो ब्राइट स्पेक पूरे का पूरा पार्टिकल नहीं होता. उसमें उस ब्राइट स्पेक के अंदर एक पार्टिकल मौजूद है, और जो पूरा ब्राइट स्पेक है वो उस पार्टिकल से निकलने वाली लाइट की हाई इंटेंसिटी एरिया को कवर कर रहा होता है. Thus an ultra microscope does not give any information regarding the shape and size of the Sol particles. It just indicates whether the particles are present or not, but it cannot give any information about the particle size or about the shape of the particles. And similarly, it can also it cannot provide any information about the nature of the material, that whether it's silver or it's gold or it's copper, whatever it is. It cannot give any information about the nature or the chemical composition of the Sol particles. The next optical property, Sol particles can be seen with an electron microscope. In an electron microscope, beam of electrons is focused by electric and magnetic fields onto a photographic plate. This focused beam is allowed to pass through a film of Sol particles. Thus it is possible to get a picture of individual particles showing a magnification of the order of 10,000. It means if we have a particle of uh, actually 10 nanometer, then we can increase the particle size of the same particle by 10,000 times on the paper. So when the particle is increased from by 10,000 times, then it can be visualized in the optical in this electron microscope. So with the help of this instrument, we can have an idea of the size and shape of several Sol particles, including paint, pigments, viruses and bacteria. These particles have been found to be spheroid or spherical, rod-like, disc-like, or even in the form of long filaments. And now the kinetic properties of sols. The first one is Brownian movement. When a sol is examined with an ultra microscope, the suspended particles are seen as shining specks of light. By following an individual particle, it is observed that the particle is undergoing a constant rapid motion. This type of constant rapid motion of the particles in a medium, constant rapid motion and in different directions in any medium, is known as Brownian motion. So the particles move in a series of short straight line paths in the medium, changing directions abruptly. This direction of the particle is changed due to the collision of particles with each other. When the two moving particles are exactly in opposite direction, then come close to each other and strike with each other, then after striking, their directions are changed. So the continuous rapid zigzag movement executed by a colloidal particle in dispersion medium is called Brownian movement or Brownian motion. And this phenomena is so named after Sir Robert Brown, who discovered it in 1827. Suspension in true solutions do not exhibit Brownian motion. It means this property of the soles can also be used to distinguish or to differentiate the soles from suspensions and true solutions. The explanation of Brownian movement was advanced by Albert Einstein in 1955 by mathematical considerations based on the kinetic molecular theory. According to him, at any instant, a colloidal particle was being struck by several molecules of the dispersion medium. Because the molecules are moving in different directions, so if we observe only a single molecule for a very short interval of time, then many other molecules from different directions can come to that particle and can strike with that particle. So the movement of the particle was caused by unequal number of molecules of the medium striking it from opposite directions. It means if a molecule is being struck by three other molecules from one side and one molecule from the other side, then it will move toward the direction given by the three striking molecules. When more molecules struck the particle on one side than on another side, the direction of the movement is changed. This figure given at this slide illustrates how a colloidal particle is knocked about a zigzag path by molecules of the dispersion medium. In a suspension, the suspended particles being very large, the probability of unequal bombardments is eliminated or diminishes. The force of the molecules hitting the particle on one side is cancelled by the force of the collisions occurring on the opposite side. Hence, they do not exhibit any Brownian movement. The phenomena of Brownian movement is an excellent proof of the existence of molecules and their ceaseless motion in liquids. It also explains how the action of gravity, which would ordinarily cause the settling of colloidal particles, is counteracted. It means the particles try to settle down, but when the particles try to settle down or start to move in the downward direction, the molecules moving from bottom to the top push these molecules in the upward direction, so the small molecules cannot be settled down under the action of gravity. So it explains how the action of gravity, which would ordinarily cause the settling of colloidal particles, is counteracted. The constant pushing of the particles of the molecules of the dispersion medium has a steering effect which does not permit the particles to settle. Here the cancellation of the particles of a suspension, the forces acting on the suspension, the cancellation of forces acting on the particles of suspension from different or from opposite sides is shown with coarse suspension particles, while in case of sole particles these forces are unbalanced. Therefore, the sole particles exhibit Brownian motion, while the particles of suspension do not exhibit any Brownian motion. The next type of the properties are electrical properties of soles. The sole particles carry an electric charge. This was also discussed in the last lecture as well. The most important property of colloidal dispersion is that all the suspended particles possess either a positive or a negative charge. The mutual forces of repulsion between similarly charged particles prevent them from aggregating and settling under the action of gravity. This gives stability to the soul. The soul particles require positive or negative charge by preferential adsorption of positive or negative charges from the dispersion medium. It means if the soul particles are negatively charged, then it's understood that they will preferentially adsorb the positively charged particles on their surface. For example, if ferric hydroxide soul particles are positively charged because these absorb ferric ions from ferric chloride used in the preparation of the soul. Since the soul as a whole is neutral, the charge on the particle is counterbalanced by oppositely charged ions termed as counter ions. In this case, these will be chloride ions furnished by the electrolyte in medium. It means the colloidal particles are suspended in an electrolyte, and that electrolyte contains the counter ions for balancing the charge of the colloidal particles. A very important phenomena in electrical properties of the colloids is electrical double layer. If the surface of the colloidal particle acquires a positive charge by selective adsorption of a layer of positive ions around it, this layer attracts the counter ions from the medium, which form a second layer of negative charges. This combination of the two layers of positive and negative charges around the sole particle was called Helmholtz double layer. Helmholtz thought that positive charges next to the particle surface were fixed, while the layer of negative charges along with the medium were mobile. So this is the concept of electrical double layer, as the name double layer is representing that this is the layer of charge. There are two layers of charges. The first is one of them is any positive charges, and the second one is of the negative charges. There are different types of the electrical double layers depending upon the explanations given by different scientists. For example, in case of Helmholtz electrical double layer, the first layer is fixed as shown in this diagram, while the second layer, which is the negatively charged layer in this diagram, is mobile layer. The mobile layer means these charges always remain in motion. They can change their position. They can move from one point to another point, while the positively charged particles are firmly fixed with the surface of the colloidal particles, and so they cannot move. Therefore, this positively charged layer in this case has been named as fixed layer. More recent considerations have shown that the double layer is made of a compact layer of positive and negative charges, which are fixed firmly on the particle surface. So now the concept is being changed from the concept of Helmholtz. Here, according to this new concept, a compact layer of positive and negative charges which are fixed firmly on the particle size, and a diffuse layer of counter ions, that is negative ions in this case, diffused into the medium containing positive ions, as it has been demonstrated in this figure as well. The combination of the compact and diffused layer is referred to as the Stern double layer, after the colloidal chemist who first realized its significance. So this difference between Helmholtz double layer and the Stern double layer is demonstrated in this figure, which is representing that in case of Stern layer, the first double layer, which consists of positive and negative charges, is very compact. Compact means the charges of these layers cannot move, they are static. While in case of Helmholtz, within the same electrical double layer, one of the layer which is in immediate contact with the surface of the solid colloidal particles, they are static, while the Second layer, which is negatively charged layer in this case, that is mobile. It means the negative ions are not fixed. However, this concept is changed in Stern layer. According to Stern, or in Stern layer, the diffuse layer is only loosely attached to the particle surface and moves in the opposite direction under the applied electric field. Because of the distribution of the charge around the particle, there is a difference in potential between the compact layer and the bulk of the solution across the diffuse layer, as shown in this figure of the electrical double layer given by the Stern. And this difference is called electrokinetic or zeta potential. It means this zeta potential is actually the difference of charge between two layers, where one layer is compact layer and the other layer is diffuse layer. The compact layer is that where the charges cannot move, while the diffuse layer is that where the charges can move. The presence of double layer accounts for the electrical properties, which are cataphoresis and electro-osmosis of colloids. It means due to the formation of this electrical double layer, the colloidal particles further show two more characteristics. One of them is named as cataphoresis and the second one is named as electro-osmosis. It has been made possible to estimate the magnitude of zeta potential with the help of these two properties. Because it means either you study the cataphoresis or you study the electro-osmosis. From the study of electro-osmosis or cataphoresis, we can calculate the charge difference or the zeta potential, which is the charge difference between the compact layer and the diffuse layer. We have explained the theory of electrical double layer taking example of a positive soul. Our consideration could well be applied to a negative soul with the interchange of the uh, disposition of positive and negative ions. It means if the colloidal particles will be surrounded by negative ions at its immediate contact, or the negative ions are directly contacted with the surface of the colloidal particles, then the very next layer will consist of positive charges and so on. The next electrical property of the soul is electrophoresis. In case of souls, if electric potential is applied across two platinum electrodes dipping in a hydrophilic soul as shown in this diagram, the dispersed particles move toward one or the other electrode. It means the positively charged particle will move towards the negatively charged electrode, while the negatively charged particles will move towards the positively charged electrode. This movement of the soul particles under the applied electric potential is called electrophoresis or cataphoresis. If the soul particles migrate toward positive electrode, they carry a negative charge. On the other hand, if the soul particles move toward the negative electrode, then they are positively charged. Thus, by noting the direction or by observing the direction of the movement of the soul particles, we can determine whether they carry a positive charge or a negative charge. It means by studying from the study of electrophoresis, we can find the nature of charge on soul particles. The phenomena of electrophoresis can be demonstrated by placing a layer of arsenic sulfide soul under two lines of a U-shaped tube, as shown in this diagram. When a potential difference of about 100 volts is applied across the two platinum electrodes dipping in deionized water, as shown in the two lines of this diagram, it is observed that the level of the soul drops in the negative electrode side and rises in the on the positive electrode side, as shown in this figure as well. This shows that arsenic sulfide soul has migrated to the positive electrode, indicating that the particles are negatively charged. Similarly, a soul of ferric hydroxide will move to the negative electrode, showing that its particles carry positive charge. This characteristic of electrophoresis is very important in case of souls due to their electrophoresis characteristic. The souls may have different applications, like they can be used in removal of smoke from chimney gases. They can be used for the removal of suspended impurities, and they can be used in electroplating of rubber on metal surfaces from latex or from a sole, and it can also be used painting of metal parts of cars from colloidal pigments. The next electrical property of the soles is electroosmosis. A sole is electrically neutral. Therefore, the dispersion medium carries an equal but opposite charge to that of the dispersed particles. Thus, the medium will move in opposite direction to the dispersed phase under the influence of applied electric potential. When the dispersed phase is kept stationary, the medium is actually found to move to the electrode of opposite sign that its own. इट मीन अपने से अपोजिट साइन की तरफ अपने से अपोजिट चार्ज वाले इलेक्ट्रोड की तरफ वो मीडियम मूव करता है. दिस मूवमेंट ऑफ डिस्पर्जन मीडियम under the influence of applied potential is known as electroosmosis. This is opposite to the electrophoresis, where there was movement of the soul particles. It means वहाँ पर disperse phase move कर रहा था, यहाँ पर डिस्पर्जन मीडियम की मूवमेंट की बात है इलेक्ट्रोऑस्मोसिस में. तो इलेक्ट्रोऑस्मोसिस इज ए डायरेक्ट कॉन्सिक्वेंस of the existence of zeta potential between soul particles and the medium. When the applied pressure exceeds the zeta potential, that diffuse layer moves and causes electroosmosis. The phenomena of electroosmosis can be demonstrated using a U-shaped tube as shown in this figure, in which a plug of wet clay, that is a negative colloid, is fixed. The two lines of the tube are filled with water to the same level. The platinum electrodes are immersed in water and potential is applied across them. It will be observed that water level rises on the cathode side and falls on the anode side. This movement of the medium towards negative electrode shows that the charge on the medium is positive. Similarly, for the positively charged colloid, electroosmosis will take place in the reverse direction. And technically, the phenomena has been applied in the removal of water from peat, in dewatering of moist clay, and in drying dye pastes. Although there are some more properties of soles, but those properties will be discussed in the next lecture. In this lecture, we finish over here. However, there is an assignment for the student that they have to find out the different colors of gold soles as a function of particle of colloidal gold particles. In this lecture, I have discussed about silver sole, that if silver soles have different size of the silver particles, then the sole will exhibit different color. Quite similarly, the color of the gold soles also varies with the variations in the particle size of the colloidal gold particles. So students have to search out the particle range and their corresponding colors when they are dispersed in water. This can be found from any research article, or this can be found from any book as well. So whatever source is available for the students, they can find out from there, and they will have to give a reference that where from the informations were collected. If there is any internet source, or if there is any book, or if there is any research article, or even if there is any review article, whatever the source is, students will have to give that reference that from this source these informations were collected. The second is a very short assignment. Students have also to prepare a comparison of electrophoresis and electroosmosis. These two characteristics I have discussed in this lecture. It's very easy to compare these two characteristics from their origin, from their basic concept, and from their application point of view. So that is the end of this lecture.